Hello, this is Greg Risterman from Olympus. I'd like to welcome everyone today to this webinar titled The Basics of Total Focusing Method, TFM. In this webinar, you'll learn the basic principles of the total focusing method and full matrix capture, or FMC, found in the new OmniScan X3 flaw detector, including advantages and limitations. New concepts such as wave sets, amplitude fidelity, and TFM grid resolution will also be covered. Our presenter today is Dali Suisi. Dali is an NDT expert specialized in advanced applications and training. He holds a bachelor's degree in engineering and a Master of Science degree in applied science, and is a certified UT and phased array UT Level 3. With a broad range of international experience, he has participated in numerous inspection projects in the nuclear, oil and gas, and steel structure industries. This informational webinar has been scheduled for approximately 1 hour. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the presentation. If we're not able to get to your questions during the live webinar, they will be addressed personally either by email or phone after the event. Now, without further ado, I'd like to turn the presentation over to Dali. Dali, take it away.
Thank you, Greg. Hello, everyone, and welcome again. I hope this webinar content will meet your expectations. Let's see today's agenda. So during about 1 hour, this webinar will discuss FMC TFM basics. However, it will be in inspection context. I will start with an overview of FMC TFM theory. Then I will present the propagation modes and give you the main inspection setup tips. Advantages and limitations of this technique will be discussed too. And at the end, we will see quickly some TFM applications. As you certainly know, a few months ago, Olympus launched the OmniScan X3 that supports TFM technique. It took us some time, but it's worth the delay, and today I will try to prove it. Since few years, TFM is being used and demonstrated in some specific applications, mainly at 0 degree, in contact, and simple configurations. However, it remains very limited, especially because of lack of knowledge, complex theory, and the kind of over-marketing. Some of you probably know what I'm talking about. I hope this webinar will help to improve your confidence in TFM and give you some tips to include in your future procedures. Let's start with the basics of FMC TFM. Actually, FMC stands for Full Matrix Capture, which is a data acquisition process. Pulse receive sequence designed to obtain a large amount of waveform data from a single phase array probe. Data is collected by pulsing one element and receiving on all elements. This process is repeated until each element is pulsed. Firing sequence creates A-scan data for every element set up to receive. Now we will take an example of a probe with 6 elements that is in contact with a steel block with an SDH indication. Actually, this example is shown on a video in our website. Just go on olympus-ims.com and go on resource and you will find this video. But I took some slides just to explain the basics of TFM and FMC. So this example, as I said, we have 6-element probe in contact with a carbon steel block that has an SDH as a reflector. The FMC acquisition starts with pulsing the first element and then receiving with all the elements. This allows to collect 6 A-scans information for this firing receiving sequence. So we fired 1 element and received with 6 elements. We obtained 6 elementary A-scans. You can imagine if we had 32 elements probe, so we will fire 1 and we will receive with the 32 elements, and then we will create 32 elementary A-scans. Such way, we start building what we call the matrix of elementary A-scan, thus full matrix capture. So we will place our A-scan in this matrix. And to make it easier, so we can use the colors. So we can represent the different amplitude of the signals by colors, where the red is being the highest amplitude and the light blue the lowest, just like we represented in phase array. So now we collected the data from the first sequence. So firing element number 1 and receiving with the 6 other elements. We can repeat this sequence with all the other elements. Like now, this is the second one, till the last one. And we obtain this full matrix data. Another way to represent the FMC or the collected A-scans is that way. As you can see here, we have 32 A-scans. 32 A-scans means we use a probe of 32 elements. And it corresponds to the first sequence, so firing one element and receiving with 32 elements. And as you can see, we can obtain the colors as well, just to facilitate the view of all A-scans in one figure. So the green colors of the map shows us the collection or the representation of all A-scans by colors. Now we have the FMC. Let's move to the TFM. TFM is the total focusing method, which is an acquired data processing. TFM is an imaging technique and should be considered separated from the FMC process. TFM takes the waveform data from FMC process and arranges the data in the image grid or zone that will be defined actually by the user. The image constructed in the TFM zone is based on time of flight, element spacing, and the proper measurement mode. Let's go back to the acquired data or to the example that we just saw in the FMC. Now we have the full matrix capture, and the user will select a zone and reconstruction path or waveset. Here we have the grid just under the probe, and we will use a waveset of LL. LL is longitudinal, longitudinal. So the user can select different wavesets. Here, since we are in contact using a probe at 0 degree, so it's easy to use the longitudinal, longitudinal, or longitudinal, longitudinal 2 times, means 4L. So LL is one of the available wave modes that will be discussed in the next section. The instrument then selects the right combination of delays and sum in the elementary A-scans to provide the maximum focus at a given point in the grid. As you can see, to make it simple, only the SDH indication area here was rebuilt in TFM with LL wave mode. So again, TFM is the process of the acquired data with the FMC, and it is based on what the user is selecting, the waveset, the zone, and different other parameters that we will discuss in the next section. So here we talked about the LL, longitudinal, longitudinal. So let's go in details in the explanation of the propagation modes. TFM reconstruction using FMC elementary A-scans is based mainly on the time of flight calculated according to the inspection mode, pulse echo or self-tandem, and the selected wave type, longitudinal or transverse. And here we have two main modes, pulse echo, which can be TT, T is for transverse, LL for T or for L, which is like standard phase array. And here, part geometry variation could affect the precision and the accuracy of the provided position of the detected indication. However, it's very rare that we will see a complete miss of the indication. So we can see a different position. However, we still have a good detection. Self-tandem mode, 3T, TTL, LL, etc., yields additional scan sets compared to standard phase array. However, results are very sensitive to geometry variation. So if in pulse echo mode, I say that variations could affect the accuracy of the position, however, it won't affect the detection itself. In self-tandem mode, The variation of the geometry could affect the detection. We will see that later. Actually, this slide is just to simplify the difference between pulse echo and self-tandem. Persons who are used with AUT and zonal discrimination technique know that for G bevel, for example, it's not possible to use pulse echo technique. So we use a pitch and catch or self-tandem mode. There are 10 modes available in X3, 3 in pulse echo and 7 in self-tandem. The choice of the right one will be explained in the next section. Actually, here in pulse echo, we can find LL, TT, 4T or 4L, and in self-tandem, we will have 7 different wavesets. The main one or the most interested one here are the 3T and the 5T. Now, let's go in deep with the setup in TFM, how we can make a setup in TFM, or what are the important parameters to consider when creating a setup in TFM. Let's start just by a quick refresh about the standard phase array scan plan. First, we have to define our part or weld. We have to select our probe. Then we select our wave mode, shear, longitudinal or transverse or longitudinal. Then the scan type, sectorial, linear, or compound. And then put the right scan parameters. When we talk about focal lows, the number of elements per focal lows, the focus, the angular range. Are you inspecting from 45 degree to 70 degree in sectorial setup, for example? Resolution, index offset, etc. Sometimes, after making this scan plan, you see that you are not covering in the right way your weld or your part, so you will decide to change the probe maybe. Now, let's see the scan plan in TFM. And here I'm introducing a new concept, which is the modeling. And at the end of this webinar, I hope that you will understand the importance of this modeling in a TFM technique or in TFM inspection. As for phase array, we start with the part or the weld definition, then the probe selection. And instead of selecting a sectorial scan or linear scan or compound scan, here we will select a zone. This is what I'm calling the zone setting. Then the inspector should select the wave set, TT, 3T, etc. And here there is a question. Which wave set he will select? What is the right one to use? We will try to answer on that question later. Flow definition, planar or spherical? What is the expected angle if it's planar? And then the other new concept we are introducing here is the aim. Aim and sensitivity index evaluation, and we will explain the aim concept later. And in the 7th step, we will define or we will evaluate our amplitude fidelity. I will just talk a little bit about the modeling in TFM and why it is crucial. Actually, the proper wavesets are very critical for detection. Many wavesets are available. Which one to choose? The type of flow influences waveset selection. The orientation of the flow. The depth of the flow also has an importance. Part geometry, curvature will change waveset's results. And also the focus is expected to be everywhere in the zone. But of course, there is a physics limit, which is the same in phase array or in UT. So we cannot focus beyond the near field. So to consider all these parameters, we need something, we need a concept that modelize the inspection or which will simulate the behavior of our wavesets or of our waves inside the material in the specific zone. Talking about the zone, so the first thing to set would be the zone. The TFM zone is the area of the part that the technician chooses to view as image. It's your area of interest. This is adjusted by technician and can be moved anywhere within the part's volume. Images are constructed in the zone grid using the pre-selected wave mode and the time of flight of the FMC data. Here, just an example of how we are setting the zone. Actually, it obeys to the same rules of phase array. So we have our center line, and we have our negative and positive index, and of course the depth. So the technician will just put the zone at the right area of interest, and it can be easily moved on the right or on the left. It can be even under the probe itself when there is no cap. Just here, note that the OmniScan X3 can offer us a resolution up to 1024 times 1024 pixels. Now we selected our zone. We have to select our right waveset. Which one we will select? So let's see an example. Here we have a root crack, and we will see how it will be detected using 4 different wavesets. On the left, we have LL mode. As you can see, we can barely see 2 very, very slight indications. On the right, we have TT mode, transverse, transverse. In this figure, we can see that we have the bottom corner of the root crack, and we have a very slight indication coming from the top tip. Now we look at the 4T on the left. We can see that we have only one indication with a random orientation. So we cannot say that there is a crack there. However, on the right, with the 3T mode, we can see clearly that there is a straight indication that is similar, or that is giving us an idea about the nature of this crack, which is a root crack. So here, in conclusion of this example, TT mode, 3T mode, is the right mode to detect root crack. However, could it be as good for example, a sidewall of fusion? So here we have a lack of fusion. On the left, we have a 4T mode. And you remember that this mode was not suitable to detect root crack. However, it's good here for lack of fusion. On the other hand, the TT mode that was very good for the detection of root crack is no longer good for the sidewall lack of fusion. So usually, actually, in most inspection conditions, we have a presence of different flows. So what is the best wave set to select? To answer on that question, Olympus brought a new concept, which is the AIM. AIM for Acoustic Influence Map. This tool helps the user to select the proper mode for the inspection and understand the effects for a given flow. AIM is a semi-analytical model that predicts and maps the amplitude sensitivity for TFM inspection. It accounts for probe frequency, element directivity, transmission reflection coefficients, geometric beam spread, material attenuation, and the directionality of the flow. Here, it's a screenshot coming from the X3. And as you can see, we set a 4T mode, a pulse echo 4T mode, and we have a planar flow at minus 32 degrees, which corresponds to a simulation of a lack of fusion. And here, we can see that there is a sensitivity index of 10.34. So using this parameter, the machine provided us a map that displays the expected ultrasonic response according to the 4T wavesets, and considering that we are looking for a planar defect at minus 32 degrees. So if we change our wavesets, or if we change our defect, we will obtain a different map. So AIM tool became very important and very essential to any inspector who wants to do a TFM technique inspection. I won't go very deep in the AIM tool since it will be presented on another webinar on March 4, and it will be presented by my colleague Emily Peloquin. So I invite you to register to this webinar to know more about this AIM tool. Now, so we selected our zone, we selected our wave sets, or we saw the behavior of our amplitude and sensitivity using one specific wave set. What if now we saw that it's not possible to detect all the defects with just one wave set? Imagine if we take back the example that we just saw, we have a lack of fusion and we have a root crack. So we need 4T, but also we need 3T. So the OmniScan offers the possibility to display 4 groups with 4 different wave sets at the same time. So here, for example, on the left, the screenshot shows a lack of fusion. It's possible to see it only on one group. On the right screenshot, we see a root crack. And here, actually, the 4 groups are displaying or are showing the root crack. However, the 2 in the top are showing it with different orientation. The 2 on the bottom, they are showing it in the right orientation. However, on the left, it seems with the right amplitude, but on the left, we are missing some amplitude. So multigroups could be a good solution when you are inspecting a part with different flows nature. Another concept in the TFM that is different a little bit from the phase array, the amplitude fidelity. This is a new concept actually. Amplitude fidelity is the measurement in dB of the maximum amplitude variation of an indication caused by the TFM grid resolution. And the influencers or the parameters that influence the amplitude fidelity are probe frequency and bandwidth, material velocity, grid resolution, and the applied envelope. Of course, there are other different parameters. The code compliance. Amplitude fidelity should not exceed 2 dB according to the ASME code. Of course, it's in the Appendix F, examination of wells using full matrix capture. Note, when the amplitude fidelity is above 2 dB, the user can either reduce the zone size, increase the resolution, or increase the probe frequency until the requirement is met. Here, let's see the resolution effect on the amplitude fidelity. A better resolution will lead to a better amplitude fidelity. As you can see the example on the extreme right, compare it to the example on the left. We have an amplitude fidelity of 5.2 dB. Then we have an amplitude fidelity of 0.3 dB. Of course, for a simple user, it's obvious that we will select an amplitude fidelity of 0.3 since also the resolution is better. So we can clearly see our indication, and if ever we want to size, it's easier, etc. Another thing in TFM, the envelope. The TFM envelope is obtained by computing the norm of 2 different TFM images. One computed using the standard acquired FMC, and the second computed using the Hilbert transformed FMC. Here, TFM envelope is not a merge image smoothing algorithm. It's a signal processing. If you look at the graphs here, on the left, we have a portion of an acquired elementary A-scan from an FMC acquisition. So this is the original signal. On the right, we have the same elementary A-scan with its Hilbert transform and the computed envelope. Here, we are not losing amplitude. We are not removing any signal. If ever we are working with no envelope and we see some small indications, very low amplitude, if we apply the envelope, there is no fear to lose those indications because the envelope is just a signal process which put the amplitude, which treat the amplitude, but do not erase any indication. There are many benefits actually for the envelope. First of all, most of people will inspect using an amplitude-based sizing. So if we are using this method, of course, we will select an envelope to see a better spot and a better indication in your scan. So you will have a better amplitude fidelity, a higher acquisition rate as well. We will see that in the next slide, but also a better possibility to make your amplitude-based sizing. Here, this is the example that shows the PRF evolution with the envelope. So on the left, we have amplitude fidelity of 1.9 dB. On the right, we have 2 dB. So it's not very different. And we have an envelope off on the left with a PRF of 12.4 and an envelope on the right with 25 hertz. So we have the double of the acquisition speed on the right one with the envelope on. Now we move to the advantages and limitations of TFM. First advantage, which is very obvious and everybody is talking about, is the indication resolution. So here we are using A32 probe in contact on a carbon steel block with small holes that could represent porosities. Two different scan plans. Here we have a standard phase array on the left, linear at 0 degree, using 12 elements per focal law and producing a linear scan. On the right, we have the result of a TFM, longitudinal mode and view. As you can see, the resolution of the different porosities is obviously better in TFM. Here we can resolve two very close indications, and we can distinguish between two close porosities. The other advantage is the near surface resolution. Of course, we are firing here in the standard phase array with 12 elements. In TFM, we are firing only with one element and receiving with the remaining element. So it's normal that at the exit of the probe with 12 elements, we will have higher energy compared to the energy that is resulting from the pulse of only one element. So the near surface for sure will be more resolved and better resolved actually in TFM than in the case of phase array, as you can see. The other advantage here is the orientation accuracy. So we are using a probe, the same probe actually, but with an angled wedge, and we are producing two different scan plans. One in phase array with a very ordinary one, and another one in TFM using TTT mode, 3T mode. So here we place our probe on a notch of 10 millimeter high. As you can see, on the left, we have our indication for the notch. Remember, our indication is a straight notch. However, here we cannot assume that it's straight in phase array case. And to make the sizing, we will need to put our cursor on the main spot for the bottom or the main reflection from the notch, and we have to look for the top corner or the tip diffraction that is coming from the top of the indication. It's not easy. We need to be very careful. Sometimes we need to increase the gain to look for this tip diffraction. Sometimes we will miss it too. However, in TFM, we can see a very straight indication that represents really the orientation of our notch, and there is no tip diffraction to look for, etc. Of course, the sizing topic in TFM will not discuss in this webinar. Now, let's talk about some limitations. The part geometry. Self-tandem mode results are very sensitive to a part thickness and geometry. So we will see that the velocity also influences the results. An error in the time of flight calculation could lead to poor detection capability. So here we have three different thicknesses, but the probe is still on the same block, so it's the same probe, the same position, the same amplitude, the same gain, and we see the difference in amplitude. So on the left, we have 21.6 millimeter thickness, which is the real thickness of the part. Then we just change it in the setup, the thickness to 24. We remained at 26 dB, but we see that the amplitude dropped. On the right picture, we see clearly we are at 26 dB, but we changed our thickness to 26.89. As you can see, we are almost missing our indication. So here the importance to use the right wave sets for the right application. I take the example of extruded pipes. If you are inspecting extruded pipes, so you should expect that the thickness is variable. You don't have the same thickness everywhere. If you are using a self-tandem mode, let's take 3T or 5T, be very careful because you may miss some indication. Here's the velocity. So 2.5 difference in value in half skip in 3T resulted in a loss of signal of about 18 dB for a vertical notch. So 2.5 actually is very small. It's only 80 meter per second difference. Here we had a high actually amplitude for the accurate photo, which is on the left. So when we saw the drop in 18 dB, it remains important signal. But in reality, imagine if you are well calibrated and you have a drop of 80 dB. So that means that probably you will miss your indication. Now let's talk about the most used or the application where we see some use of TFM already. Let's start with the high temperature hydrogen attack, the HTHA. So the voids for a stage 1 HTHA damage can be as small as 5 to 10 microns. So needless to say that the inspection requires a focused, high-resolution type of inspection. Usually, we use phase array, but with phase array, we have to focus very deep, and usually we have to make a compromise, and we have to make with the noise. We have to live with the accurate noise that we will produce when we will focus or when we will increase the dB to detect the small cracks or the early stage cracks. Also, we can use the T of D. However, T of D is very sensitive. So we want to see the difference between real cracks, the grain structures, etc. So TFM can provide an additional solution for HTHE detection. And it's already actually used in such application. H2S, or the hydrogen sulfide stepwise cracking damage. Actually, in phase array, usually we won't see the steps, the connection between the different steps of this cracking. But with TFM, it's possible to clearly see that connection and then to identify this type of defect. You know, we say that TFM will help us to characterize defects. This is a good example. Without TFM, we'll just see indications spread like randomly. We won't see the connection between them. We won't see the steps. So it won't be very easy to identify the H2S stepwise cracking damage. Another application is the electric resistant welds. Why this isn't an interesting actually application for TFM? It's due to the random orientation of the defect that we will find in such welds. So with phase array, it's not possible to detect everything because of this orientation. But using the TFM, especially using the multigroup possibility, as you can see here on the figure, on the screenshot coming from the X3, that we are using TT, 4T, and 3T wavesets. So this allows us to have a good detection, whatever the orientation would be. This example actually is for stacked lag of fusion. And we clearly see and we clearly detect a very straight indications that corresponds exactly to the orientation of the simulated notches in the block. Another example, again with the electric resistance wells for an ID overtrain. Actually, this is a misoriented crack, same thing. We use it three different groups, and we see clearly that we have the right detection, and the indication won't be exactly as of course, the ID overtrain, but it seems that it's creepy a little bit, and it can give us idea about the nature of the defect. So let's summarize. The FMC TFM technique provides for sure additional inspection solutions when set properly. The probe selection is very important for accurate results. Actually, the TFM and the FMC TFM obeys exactly to the same rules of physics than the phasor array and the conventional UT. So the near field notion is still very important. We cannot focus beyond the near field. TFM procedure should be based on modeling and waveset verification. This is very important. As we saw, sometimes you would use one specific waveset, so you can miss many indications because of their orientation or their nature. Orientation, location, and type of flow impact the results. This is for sure a problem. However, it can be resolved with a good procedure and with a good modelizer. Each inspection application requires a dedicated TFM technique or procedure that includes a detailed scan plan. As we saw, scan plan is very important, and it should be specific to one specific project or application. It can't be used for any inspection. So we reached the end of this webinar. I hope it was beneficial, and I will turn back to Greg.
Thank you, Daly. On behalf of Olympus, I'd like to thank all the attendees for joining us today, and Daly for his expertise and participation in today's event. We hope this material presented was informative and useful. This webinar will be archived on our website at www.olympus-ims.com. Everyone who registered for the event will receive a follow-up email with links to the archived presentation. That's going to do it for today. Thanks again for all your interest and taking the time to attend our event. We'll see you again for the next Olympus webinar.